Hey students, let's run through the solutions here to the exam, and you can kind of self-grade as well as learn from your mistakes here. Let's start here with the multiple choice, and maybe I should put this is exam number 1 for physics 110. All right, so express 20.0 kilometers per hour in meters per second. And so I guess the first thing is to write down the 20 kilometers per hour. And then the part I was showing you is you want to multiply by some unique value of 1 that converts it. And so that means whatever you put in the numerator has to be equal to the denominator. So you're really not changing the value, but you're changing the units. So let me start with the kilometers. So if we put kilometers downstairs and meters upstairs, the kilometers are going to cancel and we're going to be left with meters, and that's perfect. Now we just have to make sure top and bottom are the same, and so 1,000 meters equals 1 kilometer. And so you can see that that's quickly going to change kilometers into meters. Now we still have the hour issue, but the same idea then. We'd want to put hour in the top to cancel off and end up with a second in the bottom. So again, this is our unit conversion. We just need to make sure that we're multiplying by a number 1. So what's in the top needs to equal what's in the bottom. So I'll just call the top 1 hour. And so 60 minutes times 60 seconds is 3,600 seconds. So there'd be 3,600 seconds is the same as 1 hour. So again, you can see how hours would cancel off and you'll be left with seconds. And so this would give you meters per second. And so there's kind of the thinking behind it. Numerically, I guess it would work like this. We'd go 20, then we would multiply by 1,000, then we would multiply by 1, then divide by 3,600, and it looks like C would be the correct answer on that one, or the third one, I guess. There's not really an A, B, or C. Number 2 says an object is initially at x equals to 0. It has an initial velocity of -10, which means it is initially going in the negative x directions. It has a constant acceleration of a +2 along the x-axis. What is the position and the velocity? Well, maybe I'll start with the velocity, since we referred to this as kinematic equation number 1 and was only valid for constant acceleration, but that's what we have. And so we can put in the -10. We can then put in the acceleration of 2, and then it says after 20 seconds. So this would be a -10 and a +40, which makes a +30. So going to be one of these two, A or B here, or first and second one. And then the distance, I guess, would be the initial position, initial velocity times time. We call this kinematic equation number 2. In this case, it's 0 for the initial position. Initial speed is -10. The time is our 20 seconds. The acceleration is 2. And let's see, 2 times 1, that would be -200. The 2's would cancel off. 2 squared is 4, and then 2 zeros. And so that would be a position of 200. So it looks like the second one down would be the correct answer for the second question. Third question says a ball is thrown with initial velocity of 15 meters per second upward at time t equals to 0 from 0.5 meters above the ground. At what time will the height be 8.5 meters above the ground and still moving upward? So that second equation we just used on the last one, I'm going to repeat here. This is the kinematic equation for constant acceleration. And part of this is to recognize that for projectile or any kind of under the effect of gravity, the acceleration is a negative 9.8. Okay. And of course, the initial speed would be 15, and the initial height is 0.5. And we're looking for the time that it's at 8.5. And so we got a little harder math. It's a nice quadratic equation, so there's going to be two answers. And it kind of makes sense because the ball is going to be going up and then reach a maximum height and come back down. And so maybe if like this right here is 8.5, there would have to be a time when it's going up and a time when it's coming down. So there should be two times. And of course, mathematically, we have then a quadratic equation. Let's see. I'm going to move this 1/2 over to here and make that an even 8. That's a 15t. And I'll simplify if I should have put a plus sign there, the 1/2 and the negative 9.8 to negative 4.9t squared. Maybe I'll even do one more step and move everything over to the, I guess that'd be the left-hand side of the equation. So the right-hand side now equals 0. Changes the sign of these two and leaves the positive 8. I'll need a little more space, so I'll jump down to the bottom of the page here. So time equals the opposite of b. So it looks like that's a negative 15 for b, and so the opposite is a plus 15. B squared would be 15 squared minus a 4 times an a, 4.9, and a c all over 2a. And maybe I will simplify a couple of things here, starting with the harder one, which is that square root there. So I've got 15 squared minus 4 times 4.9 times 8, and then the square root of all of that. So that's going to be an 8 let's call it 26. And so if I go 15 and subtract that last, subtract the last answer. That did not work well. Let me try that again. 15 minus, let me just copy and paste it. And then divide by the 9.8. I get one time as 0.8. Or no, excuse me, 0.688. And the other is when you add them. So 15 plus, where was that? 8, there it is, copy and paste. And then divide that by 9.8. And that's a 2.37. So sure enough, two times. In fact, coming back up to this picture, the lower time would be on its way up and the higher time on its way down. So I guess I would want that one. And so looking at my options, it looks like this 2.37 works out in terms of the math, but that'd be on its way down. On its way up would be the third one there. So there we go. There's the answer on that one. All right, so number 4, a ball is thrown horizontally from a height of 1 meter. And I'm just going to split my page, as I kept telling you to do, into two pieces. A ball is thrown horizontally from a height of 1 meter towards a wall that is 10 meters away. So I guess it's going to look something like this. But the ball does not reach the wall because it fell to the ground before making it. So the furthest it could go, if this is the wall here, is 10 meters. And of course, what is the maximum speed the ball was thrown since it did not reach the wall? Okay, so I guess this part right here would be the y motion, which I'll kind of write as a same equation that we've seen for the last two problems, the second kinematics one. And in fact, while I'm here, I'll write the second kinematics one for the horizontal motion. But focusing my attention first on the vertical one right here, I guess we could say, and it depends where we put the origin, when I put it down in this corner. But let me emphasize, it doesn't matter where you put it. Sometimes we put it where you launch. Let me do that. I think I did that more times than not. So let me put it where you launch. So that means the initial position is 0, but it landed at -1 meter below, kind of like we did in the lab. And so make sure you do that below. Okay, then the initial vertical velocity is 0. And then this would be then the acceleration, which would be that -9.8. I suppose we could have just called down negative and had a positive. I mean, down positive and have two positives there. But I think it might be easier to understand that they're down, and tradition is negative, so we got the two negatives. Anyways, I guess that's a 4.9 here. And so when I cancel off the two negatives and bring it over, I get 1 over 4.9 is equal to t squared, and then t would be the square root of that. So 1 divided by 4.9, and then taking the square root of all of that gives me a time of about 0.452 seconds. Good. Now, using that time into the horizontal motion, although I guess a little subtlety here is, what do we do for the final position? Because we don't know how fast we threw it. But we do know this. We know that if we gave it just a small speed, it would only go like, say, 1 meter or less. And then if a little faster, it would be 2 and 3. So at the maximum speed, it would fall 10. Anything greater than that, it's going to hit the wall first. And that's what I mean by maximum speed. The maximum speed without hitting the wall. So I'm going to put a 10 here and say it starts at 0. And so then this is going to give me initial horizontal max speed. And then the time is the 0.452. And since it's horizontal, there is no acceleration. So this maximum speed would be 10 divided by 0.452. And since that's already in my calculator, I'll just go 10 divided by my last answer. And I'll get about a 22.1, which it looks like it would be the fourth one down there. Nice. All right, well, now the question number 5 here. 5 says, consider a potato gun that can hurl a potato with an initial velocity, and this is huge, 100 meters per second from the ground at an angle of 30 degrees from the horizontal. So this is going to look something like our projectile. And neglecting the effects of air resistance, how far away from the gun does the potato land on a horizontal ground? Now again, if you're following my advice, I suggest split your paper into 2 and go ahead and, do your Y motion and your X motion. And so here's my equation for the Y motion and identical equation for the X motion. Now this one might be a little bit easier to solve because since it says horizontal ground, it's going to land at a height of 0 and start at a height of 0. And therefore we won't have a constant with our quadratic equation. Therefore we can factor it real simple and we won't have to do that quadratic formula. So that'll be a little nicer. But other than that, it's kind of the same as the last couple of problems where we've done some projectile motion here or some involving this second kinematics equation. Some have been 2 dimensions, some have only been 1 dimension. But they showed up in both, I guess, chapter 2 and chapter 3. Okay, so maybe the harder one here is that we have to take the vertical components, and so that would be the sine of the angle. And since we've done this a number of times, I hope you'll be okay if I can just say, look, this acceleration in the vertical direction for a projectile is negative 9.8. So half of that is negative 4.9 t squared. So putting the zeros together, I get 0. And if you remember a little bit of your trigonometry, sine of 30 is 1/2. So I could probably get away without even using a calculator at that step. And this is what I mean by it factors so easy. Without a constant term, you've got a term that has a t in it and another one that has t squared. So you can just factor out one of the t's from each term. And this is why this becomes so easy. If you've got 2 things that multiply together to give you 0, either the first one has to be 0 or the second factor has to be 0. And so either this one's 0 or that one is 0. Now, you can kind of see that this first solution really is where it gets launched from, because it's not a surprise that there are 2 answers, because when you shoot this potato, there are 2 moments in time when it is at a height of 0. I mean, that's what we said here. Mathematically, we said, I'm going to put in height of 0. And so mathematically, we have where it is initially launched, it's at 0, and then when it lands again. So not a surprise then, initially launch is at time equals to 0. So not a surprise that one of the solutions is time equals to 0. It's not the one we would be interested in. We would be interested in this one. But like I said, the math just gives us all the times when the height was 0. And so that means starting off and landing. So this one we can solve by time with a little bit of algebra. And so 50 divided by 4.9 is 10.2. And now let's, like we've done on many of these problems, put that to get the then horizontal motion. And so we're looking for the x. And saying it starts at 0, it has a launch speed of, and then here's where we got to do our trig again. Just like we had to do a sine of 30 to get the vertical speed, we have to now do a cosine of 30 to get the horizontal speed. And the time is the 10.2, and the acceleration in the horizontal direction is 0. So I probably should just use my calculator, because this must be root 3 over 2. But to get a decimal, let's go 100 times cosine 30 times 10.2, and we are looking at 883, which I guess kind of depends how we do some rounding here, because it looks like there's an 884 for an option, but that would be the correct answer. And I probably carried, yeah, I wonder if I just carried that down. If I did 100 times cosine 30 times, I'll do all the decimals, copy, paste, yeah, and that would round it up to 884. So anyways, it's the third one down there. All right, I'm on to question 6. A body is pushed by 2 forces. One of the force is 100 Newton. I'll make a little graph here in kind of a 45 degrees, so that's one of them. And the other is 8 east. And so visually, maybe the thing to do is, maybe I'll just write the 8 east first, and then the 10 up at an angle. And so to get how far it is in the x direction, it would be 8 plus the 10, and this would be cosine to get the adjacent piece of 45, whereas the vertical piece would just be the 10 times the sine of 45. And so I'll do that one first. 10 times sine of 45 is 707. In fact, maybe I'll save myself a little bit of work because cosine of 45 is the same as sine 45. So I'm just going to add 8 to that. So this must be a 15.07. And then, of course, the total would be in the picture kind of like here. So we'd have an x and a y. And so we have to use the Pythagorean's theorem here, the a squared plus b squared. So in the x direction, it's 15.07. And in the y direction, it's 707. So there's the a and b. And then we can square them, add them together, and get the hypotenuse. So I'll take that and actually when I do this, I'm going to add 8. Okay, so let's take that and square it. Let's add to it and just copy and paste it and square that, hit enter, and do a square root. And it looks like a 16.6. So it looks like about the third one down for that one. Okay, nice. All right, on to number 7 here. It says, if block 1, and so here's block being on this rope, in the diagram has a mass of 2.25 kilograms, what is the value of the normal force? So here's where that free body diagram comes into play. I'll do up the hill with a tension. There would be a normal force here. There would be the force of gravity, mg, which we can divide into its components, and that's probably the hardest piece of things that were on a hillside here. This angle here is 50 degrees. You can kind of see it if you come back here and draw a triangle. That'd be 50. That would make that one 40, and then that would have to be its complement again at 50. Because going into the hillside would be mg cosine 50. Whereas going down the hill would then be mg sine of 50. Now, I suppose it doesn't really say, but there could be some friction, either static friction or kinetic friction. Kinetic if it's moving on up, static if it's kind of a rough surface of some kind, or it could be frictionless. All that they don't say. Now, fortunately, it doesn't matter because if we take a grid where the y direction is perpendicular to the surface, we know that when you add up all the forces in the y direction, which we said equal to mass times acceleration in the y direction, we know it's not moving in the y direction. Now, along the x direction, well, that's a different story. We don't really know what that number is. And so we really couldn't do anything with this equation. But we could with this one. And we will. And so focusing only on this equation, you'll see that not paying attention to the x direction, so tension or friction, we just have pushing upward the normal force, and pushing inward a component of gravity is the mg cosine 50, and that has to equal 0. So the normal force would just be mg cosine 50 degrees. So let's see, 5.25 times 9.8, times cosine of 50 comes out to be 33.1. And so it looks like the second one down. But keep this discussion in mind, because now that I gave that a lot of thought, and I'll keep this paper handy here, let's look at number 8. But number 8 is the same thing. It's the same mass, the same block, the same incline, the same angle. But now it tells me it's accelerating up the incline at 2.23 meters per second. And the surface is frictionless. And so that answers my two thoughts here about this equation, because I would say tension pulling up the hill and the stuff pulling down the hill would be the friction and the component of gravity pulling down, and that has to equal to ma. But again, they said frictionless. So I will put a 0 for the friction, but they do tell me then the acceleration, and that's perfect because they asked me for the tension. What is the tension in the rope? Number 8. Okay. So the tension in the rope then would be MA then plus mg sine 50 degrees. Or put another way, as we read the math here, the tension would have to be equal to at least this much just to balance gravity pulling it down the hill. Then there would have to be plus an additional amount to get it accelerating. So if you just had this, it would just kind of be stationary there. You'd just be holding it in place. To get it to start moving forward and accelerating upward, we have to have a little bit more. So this is the 5.25 times the acceleration, 2.23, and 5.25 times 9.8 times sine of 50. And so if I put those into my calculator, 5.25 times 2.23, add 5.25 times 9.8 times sine of 50, I get a crazy number of 51.1. And I guess that would be the third one down. Nice. Now good. So those kind of went together, and each component in the two-dimensional world. The first one was about the y component, and the second one was about the x component. All right, well, last two on the multiple choice has here a 40 kilogram plate is being pushed across a horizontal floor by a force of 240 newtons. The coefficient of sliding friction is 0.5, so there is some sliding or kinetic friction going on. What is the acceleration? So again, adding up all the forces and setting it equal to ma, we have 240 minus the frictional force equals ma. And so the frictional force is the coefficient times the normal. So besides drawing the horizontal forces, let me also draw the vertical forces. And of course, what I just applied was the acceleration and the forces in the x direction. If we also did that in the y direction, noting that it moves across a horizontal floor and doesn't accelerate in the y direction, we have acceleration equal to 0 for y, and then we got normal force up and mg. And so we got the case where the normal force is equal to mg. You guys might recall me saying many times, don't think that the normal force always has to be mg. Sometimes it is, sometimes it is not. Okay? But in this case, it is, so I can put a 0.5 times the normal force, which is mg, and so that's a a 40 times a 9.8, and then a 40 and the acceleration. So putting in those numbers, 240 minus 1/2 times 40 times 9.8, and give me a number of 44. Dividing that by 40, and I get a 1.1 meters per second squared. So the second one on the list here. And then the last one, here we have the density of air. We have a skydiver, and so I'll just kind of make a little blob. Because on a skydiver, what's pulling the person down is mg, and air resistance or drag is pulling up on the person. And we learned that that was equal to 1/2 times this coefficient, times the density, times the cross-sectional area, times the velocity squared. So there were 4 factors that went into determining how much air resistance it would be. And there is, of course, right here saying it's at terminal speed. So if I were to add up the forces in the y direction, set at mass equal to acceleration in the y direction, we can safely say it is not going any faster. It has gone so fast that what you really mean here is the mg pulling down equals the resistance back. There's no net force, and so the acceleration is 0. And so one of the things that hopefully is obvious is that in this scenario, because of Newton's second law, we can say that the resistive force is equal to the weight of it. Okay. And I thought, what were we given here? Or what are we looking for? Oh, what is the magnitude of the weight? Okay, so that's the key step. The resistance is equal to the weight. So I'm going to come back up here and then just calculate that resistance. So they say C is 1, density of the air is 1.2, cross-sectional area is 0.6, and velocity is 54, and I'll just square it. So I think maybe the hardest part is this equation, but then the second hardest part is realizing that force must be equal to the weight to get 0 acceleration. Okay, so now I can put things into my calculator. 1/2 times 1, I'll skip that. 1.2 times a 0.6 times a 54 squared, and it looks like we're at about 150, and so it looks like D there, or the fourth one down, would be the best answer for that one. All right, so now on to the free response. And they, are the same kind of category. In fact, you can probably see this one right now. It looks a lot like the projectile ones we did, except that it's not quite as simple as landing on the ground here. Here it says a wheat cannon sits on the floor in a room and shoots a ball with an initial velocity of 20 meters per second at 55 degrees from the horizontal. And by the way, some of you have a 10 on your test because I forgot to hit update. The night before I was doing the math and the 10 was not a good number to use. And I go, I'll change it to a 20. And sorry, I didn't hit update until that morning. I was like, oh no. So I graded it either way. So if you did 10 there, that's fine. I graded it that way. But 20 is a much better number. So I did hit update. I guess I'm just so used to Google where you don't have to do an update. But some of these older programs or legacy programs like Canvas, you got to update things. And these days, even Microsoft has their auto-save feature now. So, and you can do it either way. Anyways, I'm going to go ahead and solve this problem with 20. Most of you, there was a few of you in the morning, but who did this, but most of you did it with a 20. Okay, 55 degrees from the horizontal, the ball exits the cannon 1.25 meters above the floor. There's a tall vertical pole that's 15 meters from the cannon, and the ball hits the pole. how high above it. So let me just get some paper. I'll use the back of this last sheet here. But again, like all of our nice projectile motion ones, hopefully the first thing you did was kind of separate your paper into its two pieces, and you wrote out the equation for constant acceleration and position, which is the equation number 2. And again, I'll just do it twice because you want to do it for both x and y motion. Now, it looked like all the multiple choice ones, we kind of focused on the y first. And it doesn't matter what one you do first. At some point, you'll notice that you've got to complete one of them before you switch back over to the other ones. And I think during the multiple choice, that was always y. We'd solve y because for time, and then over here because we knew something about the position of y, like that one that landed on the field, the potato gun. We knew it landed back at height 0. The one that went straight horizontally and didn't quite hit the wall. Again, we knew something about the y motion. Which it's because of that I know something about the horizontal motion. I know it goes 15. So I'm going to do the x motion calculation first. And so drawing maybe a picture here. Let's see, let me not go off the screen, but get low enough here. Here's the pole, and maybe the cannon launches from right here. And I don't know if it's still on its way up or if it's gone down. I'll give it a kind of a downward look to it at the moment. But if I put the origin, this time let's put the origin down right below the ball, because ultimately it does say how high does it hit the pole from the ground. So I'm going to be measuring things from the ground. So let's put my vertical from the ground. Okay. Which then over here means it's being launched at 1.25, its initial height upward. And keep in mind, there is no right or wrong place to pick your origin. You can pick it where it's launched, you can pick it where it lands, you can pick the corner of the pole. But I think this one might be the most direct one for this case. But whether you pick the origin here or where the ball launches, you're going to get a horizontal distance of 15 and a starting one of 0. And then you're going to get a 20 and a cosine of 55 times t. And a very important step for projectile motion is to recognize there is no acceleration in the horizontal direction. And that right here allows us to then solve for time. And that's what I mean by we knew something about the x motion. So I'm going to do this column first as opposed to the other equations on the test so far. We knew something about the y motion. But if I do this 20 times cosine of 55, that means the horizontal speed is 11.47. So if I go 15 divided by that last answer, I get a time of 1.31, which, by the way, would be 2.62 if you had, of course, half the speed. So if you had the 10, you would get that for your time. Now, let's use that over here. So this would be the 20 times the sine of 55 degrees. And then the time would be the 1.31. And we've done this quite a bit. Remember, the acceleration in the y direction is negative 9.8, and so half of that makes a negative 4.9, and then 1.31 squared. And so punching all those in, 1.25 times 20 times sine 55 times 1.31 minus 4.9 times 1.31 squared. It's a long equation that comes out to be think I hit something wrong. Something bothered me there. Let's see. 0.31, 4.9, 31, sine 55, 20. Ah. No. $18.4. I'm really bothered by that. That is not what I got earlier when I set it up. Oh, yes, and I see what I did now. I hit a times right there. My bad. Okay. Let's do this. Let's clear that line. Let's go re-enter. There it is right there. That should be a plus. 1.25 plus, okay, yeah. Yeah, that's what I set it up for. Yeah. 14.3. Nice. That sounds familiar. Okay, so 14.3 meters. Good. Let's see. Let's go on to number 2. Let me get another backside. I'll do backside number 7 here. Let's see. Block. Let's see. I got it on the screen here. Yeah. So block number 2 right here has a mass of 7 kilograms. And block number 1 has a mass of 9 kilograms. Okay. Block number 1 moves to the right and horizontally and has a mass as number 2 moves down. The coefficient, so there's some friction, is 0.35. So in this free body diagram, I'm going to put some friction. It's being pulled with some tension. It's being lifted up with some normal force, and it's being pulled down by M2G. So if I were to have an X and a Y for block number 1, and likewise an X and a Y for block number 2, although number 2 is a little simpler because we're going to have just gravity pulling it down, M2G, and tension pulling it up. And there's not going to be any X motion to block number 2, but let's write these out. So looking at block number 1, the sum of the forces in the X direction would be tension minus friction equals to M1A. In the Y direction, if you add up all the forces in the Y direction, you have normal pushing up, you have M2G, and that has to equal to M2 and acceleration in the Y direction, which we know to be 0. So that gives us a normal force of M2G. And the reason that is helpful is because tension minus the friction, and friction is the coefficient times the normal, so this would be coefficient times M2G equals M1A. So this would be my system of equations for the top block as I push that into there. And now doing the same kind of thinking for the second block, of course there's nothing in the X direction, but some of the forces in the Y direction have to equal mass times acceleration in the Y direction. To keep things consistent between block 2 and block 1, since block 1, when it moved to the right, I called it positive, let me go block 2 down as positive. So I would have an M2G going down and a tension going up. And up this time is going to be negative. And so that's a little different. And that would be M2 times A. And in this case, A is that same acceleration. And that's how I'm going to tie the equations together. Because it says, what is the acceleration? Now, it specifically says block 1, but in that case, my argument is that they're the same. And this is why it can be helpful, because then I can write this as M2G minus M2A is equal to the tension, and then couple that back into here. So I got this direction with the normal and put into there, but I also got this one for the tension and put it into there. And so this is going to be M2G minus M2A, as I put it into that tension, then minus mu M2G equals M1A. Moving this to the other side, we have an M1A added to an M2A, and then we have an M2G minus mu M2G. And maybe I'll pause right there. I did go what you might call the long way, but the more complete way. But I actually set this one up, given that it was the first exam. I thought I'd make this pretty straightforward. You could have really kind of got right here from the beginning on a problem such as this, because you could have thought of this as one big object kind of bent. And when you do that, the tensions are internal, so you notice there's equal and opposite, so you don't have to worry about that. So you could have just said, well, what's pulling it is this one right here, M2G. What's stopping it is the friction, which comes from number, oh, and I think I messed up back here. Oh, I'm glad I looked at this, because that should be friction on number 1, so it would be the mass of number 1. And so that means back here, that should be number 1, and that should be number 1. Yeah, good. Glad I said something. But see, then the friction would be based upon the normal force. Did I put, there's where I made the mistake. I started calling this number 2 for some reason. Probably mentally I went to X, Y, and I kind of just clicked in my head from mass 1 to mass 2. So my apologies. This didn't come out to be a very cohesive answer. Okay, this is all about block number 1. And this should be all about block number 2. And so these should be 2 and these should be 1s. Yeah. Okay. All right, but anyways, this would push it forward. This would be stopping it. This has to do with block 2. This has to do with block 1. But then collectively, the two move together. So that's why you could have thought of this as one object, where over here the mass is the total of them, because they both move. But the only one pushing it forward is M2, and the only one opposing it from going forward is the friction from M1. And so, like I said, you could have kind of reasoned that out without quite going in much detail. But I did want to take the time in the video to go through the detail, because hopefully you're seeing what I'm doing, and I'm just doing the same thing. I'm adding up the forces and setting it equal to MA, whether it's X and Y, or whether it's block 1 or block 2. And if you really nail that down, then there's no problem you can't do. And so going into chapter 6, which by the time you get this video, you probably have been struggling with 6, you'll see it can get a lot harder. And so it's this general technique that will serve you well. Okay, well, let me put in some numbers. Block 2 is 7 kilograms. So 7 times 9.8 means that we've got about a 68.6 pushing it forward. Stopping it would be this 9 times 9.8, and then, times the coefficient of friction, which was 0.355. And so it's being stopped by about a 31.1. The two together collectively is the 9 and the 7, and so that's 16. So if we come up here and grab that 68.9 and subtract the 31, the net force pushing them together then is 37.3. And then the acceleration then is divided by 16. And so 2.33 meters per second squared would be the acceleration once you had gone through all these details. So again, sum of the forces X, sum of forces Y for block 1, sum of forces X, sum of forces Y for block 2. Manipulate all the equations. In this case, put the Y from 1 into the X from 1, and put the Y from 2 into the X from 1, and you get that, which kind of what you would expect. Think of it as one big object. So this one was set up much easier than could have been, and you could have thought of it as one big block, but that doesn't always happen. Those are only the easy ones. All right, well, hope that went well for you. All right, well, let's do one more here. Let me do the backside here of number 8. And this one here is one that has a non-constant acceleration. And that's probably the hardest part of this, is to recognize that an equation that would looking like this, final initial plus acceleration times time, can't be used. The one that looks like this can't be used. Those were all of our constant kinematic or constant acceleration kinematic equations. And so we got to go back to our calculus. And so you recognize here that the acceleration, and I'll just write it without the units, is 3t. In other words, it changes with time. If you made a plot of acceleration and time, it would be just a straight line, right, with a slope of 3. And so that means it changes. So none of these equations for constant acceleration could work. All right. So with that in mind, we have to recognize that the acceleration then integrated, or I guess I should say the velocity, would be equal to the integral of the acceleration. So in our case, the acceleration is 3t and dt. So when we do that, we can pull the 3 out in front of the integral sign, and then we get t squared over 2, and let's not forget plus a constant. And studying this well, we'll see that if you put in time equals to 0, so I'd say velocity at time equals to 0, this first term would be 0, and you would just get c1. And so a good representation of this constant of integration is the initial velocity. So back in your math class, you probably just left things in terms of a constant. But in a physics problem, we can come back and say, well, that physically represents the initial speed. And so as we read it carefully, it says it starts at rest. So that's a 0. So that reduces our equation a little bit easier. And it allows us to answer the first part. It says, what is the velocity and position at 20 seconds? So if I do 20 seconds here, let's see, 2 squared is 4, so that'd be 400 divided by 2 would be 200. 200 times 3 is 600. And so there's half the problem. And then, of course, the next step is to get the position. And the position is the integral of the velocity. So we got to integrate again. So we've got 3t squared over 2 dt. And the 3 over 2 I'll leave alone. And then when you integrate, you take the time and you raise the exponent, divide by the new one. And then don't forget some kind of constant of integration, which in this case I'll call it C2. Can simplify this a little bit, and I get time cubed over 2, and then that constant. And like we did when we did the first integral, you might want to stop and think about it. What is the position when time equals 0 would give me 0 plus C2. So a good physical interpretation of this mathematical constant is its initial position, which, coming back to the problem, clearly says it's a 17. So the equation for position must be t cubed over 2 plus this 17. And now to finish this problem and the test, we can put in our 20 seconds. And so 20 seconds cubed divided by 2 plus 17. Let's see, 2 cubed is 2, 4, 8. So 8 and 3 zeros divided by 2 must be about a 4,000. And then 4,000 added to 17 is 4,017. And I won't make a big deal of significant figures, but you might want to put 4,020 for the final answer. Ta-da! All right, well, I hope that wasn't too confusing when I messed up the 1 and the 2 there. I apologize. Or, what was another mess up I had? Oh, yeah, and I put that in the formula. I put a times instead of a plus. But other than that, hopefully this helped. Hopefully you learned something. If you got anything wrong, it makes more sense to you now, because you'll need all this information moving forward. And hopefully it wasn't talking too fast. I did want to try to keep the solution under an hour, and it looks like I just made it by 3 minutes. So take care. Bye.